Hello, students. The next part. So, just we did something with those vector fields, the calculating potential and looking if a vector field was conservative or not, and go so on. The next step is in certain sense integrating vector fields. And I find it a little bit strange term, because what can we now integrate to vector fields? Here you have some vector, you have some vector f. It depends on x, y, and z if you are in R3. And then it has several components. It is a vector, and what to do? Now, what shall we see? That with that term integrating vector fields, we will most of the time we will manipulate the vector fields. So you will manipulate on some way that vector field, and then we do something with that vector field. We take an inner product or something else, or what we can do. So do something else, and if you have done something else, you have something with that f, and you get some function which for instance, you can take an inner product, or you can do something else. You can add the derivatives of those three components together, or some other strange thing. But the result will be that you have then some function. You get some function, and of three coordinates, and that you want to integrate in R3, integrate over a volume, or over a surface, or a line. But I think that keep in mind that you will have to do to manipulate that vector field in some way, that you have some function, just some function which if you fill in x, y, and z, you get some real number, and that you will integrate over some volume, some surface, or some line. That is the integrating vector fields. And let's see what we can do. And then the idea, keep that also in mind. Integrate over some domain, and then you want to do it on an easier way, and result will be some integral over the boundary of a domain. So there is very much that there will be asked to integrate over some domain, and then you do some manipulations, and the result will be that you have some integral over a domain, over the boundary of a domain, and which will be less easier to do than the original integral, and that easier to do than original integral. So that will be what we want to do. So we will do, you will get some integral. They ask you to do to integrate over some volume, for instance, over some ball, over some a ball, and then you do something with them. And if you have done something with that vector field, the result will be, for instance, an integral over the boundary of that ball, or over the sphere. Now and then maybe the integral over the sphere is easier than the original integral. And yeah, we will see. We will try. We will what we get out of it. I don't know at this moment. Let's see. Um, First of all, line integrals. So, what to do then? So there is an integral. You have some curve, and you have some function ds. So you integrate a function over that curve. C is a curve, and most of the time we assume that you have a curve xt. So your t is your parameter, and that t is between certain values a and b. So some bounded domain, and you have some curve. T is a parameter, and then you want to integrate that function over that curve. Now, what to do? Well, what can be that t, the s term is a little bit like yeah, for some little distance. But be careful, we do everything we do dimensionless, but and so so be careful by using that words distance and velocity and so on, but we will do it just by to have some idea what we do. A little distance. Now if we know that curve xt, we can differentiate it, and if we differentiate it we get the velocity. And if we multiply the velocity by dt, and you take the length of the velocity vector times dt, you get a little distance. Yeah, velocity times dt gives you a little distance. And then be careful, this is a vector, and I want to do something. I want to integrate a function over the thing, so I have to do something with that vector. From that vector, with a vector, I can do nothing. The only thing I can do is calculate the length of that vector. And if you have the length of that vector, you have again some number, and there you can do something with. So there's some length. And also here, be careful by using those words length and so on. And the t-like of the time, but we have no time because everything is dimensionless. But look for that t. You can think yourself, let the t be the time and let s be the distance. Okay. Now what can we then do? So if we have then that curve of that integral which is staying there, and we know that this curve can be parameterized by xt, now then we can write down the integral of from a to b, the function you fill in that all the points of that curve, and you multiply by the length of the velocity vector times dt. And then you have here your ds term, and here you have your integral. Here you have your line integral. You can also say you know integrals as they are introduced if you have in a b, and here you have, for instance, the x-axis, y-axis, and your y is equal to fx. Now then you cut your domain into pieces, and you were calculating the area beneath the graph, and all those areas you made a summation of up, and you have your integral then, and that is told to you, take the integral from a to b fx dx and everything, and you have your area beneath the graph. And I am also here area, here my function is positive, but if my function is negative, I can also get some negative value out of it, and an area, area is not, is most of the time always positive and can never be negative. But okay, this is for the idea. Now, and now we can do that the same in R3, that curve xt and your t between a and b. Now you can cut up, you can cut your, here if you have here the parameter t, you can cut that into pieces, and then in what in R3, what do you do? Now you have your x, y, and z axis and the origin. You have your curve here, and you see from, if you fill in those values of t, here you're starting with xa, here you have xb, and then you see, for instance, if you fill in the first step, now then you get here the first part here, and you go so on, and now you want to calculate the integral of that. Now what to do? You just take the function in xa, and then you multiply by that little distance, by that little part here, that distance, and that distance times delta x, times let we do a delta s. And how do we get that delta s? That can be, we can think as a distance, and so we calculate the velocity in xa, and then we multiply by a little step in dt. Here you have your dt, and here is your ds term, the delta s term. And so we can go on for every part of your parameter, and then you have always that little step ds, and that is nothing else than the velocity somewhere times dt. Now, and so you can add all those things together, and if you add everything together, you get your integral, and we have just written it down, and that gives you that formula, the integral. If you integrate a function over your line, you get the integral from a to b. Now you fill in everything on your line times, and then don't forget to calculate the velocity times dt. And so you have this one here. Now, that is the first step, the line integral. And now I'm so near to some other results that I think to myself, what shall I do? Shall I stop or shall I go on? And I think I go on, but we get a very, and then you see directly what I mean, that we are very much coming back to those integrals like here. What to do now with line integrals of vector fields? What to do with that? Here we have just we did just we integrated a function over some line. And now we will we want to do a vector field over a line. Now what to do then? Now let's first of all write down how we write it down. Now we have again an integral about some curve, and then there is written some vector field, and then an inner product dr. And so here you have some, if you are in R3, a vector with 3 components, and the dr has something to do with that xt. This is your curve. Your t is between some a and b, but and this one is also an element of R3. But this has to do with distance, because you can see this integral as that you calculate the work done by that vector field. And the work done by a vector field, work is always a vector field times distance. So work, vector field times distance gives you the work. And that, yeah, this is not nice written down, but just for the idea. So you were calculating the work done by the vector field. Now, if you have that curve xt, you can differentiate it, you get the derivative, and we have the velocity vector. Now we have a vector. Be careful, velocity vector, just as we did before. Now, and what can we then do? That step in the space we can write down as the velocity vector times dt. And here I have just a multiplication. This has nothing to do with the inner product. This dt, that is some real number, but this one is an element out R3, that you have your vector. Now, and so what does this integral, so what is the integral if we write it out on some other way? We get the integral from f, you fill in the points on that curve, and then you take the inner product with the vector, with the velocity vector times dt, and you have your integral, because your parameter goes from a to b, you have the integral from a to b. And be careful, this is inner product. Okay, now, so we have already a little bit reformulated our expression on the left hand side to some better thing, because we have now the curve we have filled in the vector field, and we have taken the inner product with that velocity vector. Okay, but now, if now your vector field, if that is equal to the gradient of phi, what can we then do with that right hand side? Now then we see the following. Then the and that I do on the next page to get the result together. Then so I am integrating the vector field over that line. Now, and we had written down, this is the integral of that vector field filled in the points on the curve, and we take the inner product by the velocity vector dt. All right. And what was assumed, or what did we know? We know that the vector field was the gradient of some potential. So we can fill in that integral, and so we have the integral from a to b, and then we have that gradient of the potential, and then fill in the values of that line and take the inner product with the velocity vector dt. Now, and I think that we can calculate here this inner product, that we can calculate here the primitive function of it, because what is staying there is staying the partial derivative of phi to x in the point where you are, times the first component of the velocity vector, and so we can write this completely out, and we get the partial derivative in the y direction. You fill in the thing and then times the y component of your vector of your line, and this one differentiates to the z variable times the derivative of z dt. Now, and I think that we can also write this as some derivative, and that is the derivative of that potential where you have filled in that line. Yes, and here on the left hand side, that gradient of phi xt times the velocity vector is nothing else than the derivative of the gradient of the gradient of the potential where you have filled in that line. Now, and so we make some step. We have made rewritten that expression, that blue expression there, and what do we get out of it? We get out of it the integral from a to b, and then the derivative of the potential along that line times dt. Now that is an easy way to calculate because that is the potential of xt between the the boundaries A and B, and what do we get out of it? The potential in the end point minus the potential in the begin point. And so we have really an easy expression for it. So if f is your gradient of some potential and you want to calculate that integral f inner product with dr, you see that you have the potential in the end point minus the potential in the begin point. So if your f is equal to the gradient of some potential, then you see that that line integral gives you this expression here. And now that is in a certain sense so and I hope now that I told you from you are going to the boundaries and you see here that you have some integral. That integral you take from some expression, and what is the result? You do something with it and you get the endpoints. The endpoints of that line. And you could think as the boundary points. And so you see that you have here a first, of not a first result, but for vector fields you have a first result where you are manipulating. If your vector field has a certain form, and in this case that you know your vector field is the gradient of some potential, that you know that if you calculate the work done to come from the one point to the other point, that is nothing else than the potential in the end point minus the potential in begin point. No. And so we can and so if you have and this we called that f is conservative. And this means that f is conservative. And you see also that the work done does not depend on how you go from the begin point to the end point. It's independent of the way, the path, how you go from the begin point to the end point. Okay, now I like to stop here with this one here. This is our first result, a vector field integrating over some curve. If your vector field is conservative, you have the potential in the end point minus the potential in the begin point. Now keep that in mind.